Yes, good morning. Today we will discuss about the steady state stability, which is also called as small signal stability. In the last class, we have discussed about the classification of the power system stability. So usually power system stability will be classified under three categories. Your one is rotor angle stability and frequency stability and voltage stability. Again, in rotor angle stability, we have two classification. One is steady state stability and one more is transient state stability. Now we will move the concept on steady state stability. So basically, what is steady state stability? It is defined as the ability of the power system to maintain synchronism in the event of a small disturbance. So to maintain synchronism or to maintain normal state or to maintain equilibrium, all are same. So basically it is defined as the ability of the power system to maintain synchronism in the event of the small disturbance. So the steady state stability depends on what factor? It does not depend on the nature of disturbance. It does not depend on the type of disturbance. It does not depend upon the location of disturbance. Then on what factor it depends? So it depends on the initial operating point. Let us take an example of ball which is in hilly area. Let us say take example of ball. So and this is my hilly areas. Okay, and a small disturbance is sufficient to move from the initial point. So when a small disturbance occur to the system, so it may lose its stability. So it may be of initial operating point. This is a ball and this is an initial operating point. If any small disturbance occur in the system, there may be a chance of the loss of synchronism. Maybe the stability loses its synchronism. So this is a brief example for this. In the same way, in power system also, if the operating point is not defined properly, so there may be a chance of losing the synchronism. So my steady state stability, which is also called as small signal stability, so it's purely depends on the initial operating point. Now let us see, this is a power angle curve. Now this is my initial operating point delta naught and this is my PM. At initial operating state, my acceleration power will be at 0. 0 means it is a constant speed. So let us say this is a delta naught is my initial operating point, and at this point you will get the maximum power at delta equals to 90 degree. That we will discuss later. Now at initial operating condition, my PM equal at initially the system operating in steady state. Under steady state condition, the implication is that my mechanical power input is equals to electrical power output. So here I taken the initial operating point, it is delta naught. So how to get delta naught? So how to get delta naught? So PE equals to P max sine delta. So we know that. So PM equal P, whereas initial operating condition at PE equals to my PM, that is my mechanical power and electrical power are equal. Instead of PE, I will write as a PM here. So once you write the PM, so PM equals to P max sine delta naught, where delta naught is an initial condition. Now I can write delta equals to sine inverse PM by P max. So what is this P max? We have studied in the last class. So it is a constant we have taken. P max is generated EMF, EB is my infinite bus voltage, and X is reactance between them. However, we have written for the swing, we have written for the power angle equation for that EG by X, the same thing here. EG is my generator EMF, VB is infinite bus voltage, and X is reactance between them. Now, remember that my operating point of the generator. What is my operating point of the generator? So I will take operating point of the generator is delta naught. Delta naught means initial operating point of the generator. Then what will be the W naught? W naught is synchronous speed. So under steady state condition, we will assume that W naught equals to 0. That is synchronous speed equals to 0. 0 means here its speed will not be 0. The speed will be constant. That condition we will be taken as 0. So under initial operating state, I can say that P equals to P max sin delta. So this delta naught is initial operating condition and omega naught is my 0. 0 here, it is not speed, it is a constant speed. Let us assume that delta is disturbed by a small change in angle delta. Now under initial operating condition, under steady state condition, so my acceleration power will be the mechanical power will be the same, Pa equals to 0. But when a small disturbance occur in the system, here you can see when a small disturbance will be occur in the system, my delta naught will be increased to delta naught plus del of delta. My PE will be increased PE naught plus delta. Assume that your mechanical power will be the constant. In the last class, we have also discussed keeping the mechanical power constant. As you are increasing the electrical power, there is an increase in delta. So now let us assume that due to some disturbance, my delta naught is increased to delta naught plus del of delta and PE naught plus delta power. So when it is increased, what will happen to the system? Yes. Now usually acceleration power will be the difference between the mechanical and electrical power. Under initial condition both are same, Pa is 0. Now P is changed to P naught plus delta P. So that means now Pm will be the remains constant, so no change in the mechanical input power. So I can write my Pe as Pe naught plus delta P, change in electrical power. Now acceleration power will not remain 0. That means it will not remain constant speed. So now it will not be equal to 0. This will be changed. So now the change in acceleration power is going to change the value of the delta. Now as your acceleration power is increased, the delta will be increased. Whether this change, the problem statement is here, whether this value change within the bounds or whether this going to be unbounded. Now whatever the change in the delta, whether this delta will make the system as stable or unstable. That means whether it will be bound or it is unbounded. So that why we need for the study, if there is a small change in delta, so if there is a small change in delta, whatever the parameters, whatever the system parameters are so chosen that your system is able to withstand these minor changes. If it not, the whole parameter choice is wrong. Again we need to rethink and again you need to reframe the basic equation, basic parameters. So now as per the swing equation, so this is not, yes. Now we'll see mathematically, 1 minute. Yes, this page. Now we'll see this mathematically how delta changes with respect to the time. Yes. Now we will see mathematically how your delta changes with the time. So linearizing about the initial operating point. Now assuming that this is my power angle equation, this is my power angle on this is my power angle curve. Since this is in delta, since this is in delta, since this is in delta, so delta is a non-linear function. So here my delta is a non-linear function. Now I want to make it is possible to make non-linear function as linear function. My sine delta is a non-linear function. So what I will do is I will take a piece of work in non-linear function. I will convert it into as a linear function. Now see this. As my delta changes and my PE also continuously changing. So the change in delta here from this point to this point, I will take it is an this part I will take for analysis purpose, and this I will take it is a constant. Now as a constant means I will consider this is a linear function. Now P equals to P max sine delta, this is non-linear function. Now assuming the slope is a constant. Now delta P I can write, it is dou PE by dou delta into delta of delta. So del of delta. So where my this del PE by del dou PE by dou delta equals to dou PE by dou delta. So this, what is this indicates that change in the electrical power, change in the electrical power will change in the angle. So why this 0 means I am evaluating at delta equals to delta naught. So let us consider this equation. Let us see here. Now assume that this is in my initial operating point delta naught, and this is my change in delta, So this portion, so this portion I will be using for analysis purpose from here to here. Now this is my delta naught and this is my change in delta. This is delta naught plus change in delta. Now this portion, whatever this portion, I will consider it is a constant. So for this portion I am considering as an initial operating condition as delta naught. This is my slope will be constant. So at this condition I will treat it as an my initial operating condition will be of delta naught. For this portion, I will consider it is an initial operating condition as delta naught. So that's what he had been given here. P equals to P max sine delta. So evaluating at delta equals to delta naught. So dou PE by dou delta equals to P max cos delta naught. So evaluating this at initial angle. So because of that I taken here it is naught. So what naught indicates, that signifies that I am evaluating my slope as a constant, that will be initial condition will be of at delta naught. So we in last class we have studied about the swing equation. So what is the swing equation? Says that md square delta by dt square equals to pm minus pe, that is under steady state condition. So that is non-linear function. Now what I will do is that function I will consider it is in linearized, I will do that as linearized function. So I can write md square delta md square del of delta by dt square equals to pm minus I will make pm as a constant, and my PE instead of PE I will write the change in the power PE naught plus del PE. So at the initial operating condition my PE naught equals to PM. At the initial operating condition my PE naught equals to PM only. So this and this will get cancelled. So what I mean to say is at initial condition my PE naught equals to my PM. So I will instead of PE naught I will use PM in the equation. So now it finally becomes del P. This and this will get cancelled. Now let us linearize as like above. So what I will get is md square del of delta by dt square. When I change this where I use dou PE by dou delta not del of delta equals to 0. This equation I have used here. So del PE I substituted del PE this RHS side equation here. So here I substituted. Now if I transform to this LHS side, then it plus minus becomes plus, so it becomes 0. RHS becomes 0. Now, yes. Now the characteristics of the equation of different since this is an second order equation. It is a second order equation. I can write this in terms of characteristics of root of the equation. This you learned in network and control systems. The same thing I will put in form of the characteristic equations. Yes, here I can write. So instead of I will write ms square plus del PE dou PE by dou delta equals to 0. This is my characteristic equation of the differential equation. That differential equation I will put in the form. Now if I make for the s becomes positive plus or minus, it is of square root of minus dou PE by dou delta divided by m. This equation del PE by dou PE by dou PE by dou delta is called the synchronizing power coefficient. It decides whether my system is stable or unstable. Now let us see the nature of the roots when we will decide it is stable or unstable. Now S equals to plus or minus dou P by dou E equals to, it is dou P by dou PE equals to 0 divided by M. It is not E, it is my delta. Right. Now I want to check the condition for the stability, whether the system is stable or unstable. When the system will be stable, when the system will be unstable. Let us assume that the roots of the equation S1, S2, which we will say these things of the character roots of the system, and my response depends on K1 E into S raised k1 into e raised to s1t plus k2 e raised to s22 and so on, where k is implies that it is a constant. If this response has to be bounded, there are two ways. If this response has to be bounded, we are having a two ways. All the exponential must be dialed down to 0 or exponential should be bounded. So we will see, let s will be the complex root. Let s will be the complex root. Let us assume that our system s equals to sigma plus j omega. So this in exponential form we can write, e raised to s2, e raised to omega, e raised to sigma t, e raised to j omega t. Now let us see how this will happen. Now if my sigma is greater than 0, now my oscillations will be like this. So what is the output stability, or what is the output? My as sigma is greater than 0, it exponentially increases. That means increasing oscillation. The implication of this, the result of this, so the oscillation is exponentially increasing. Now if sigma is less than 0, here my oscillation is decaying exponentially, it is decaying. So now if my sigma equals to 0, my oscillation will be sustained. You will get sustained sinusoidal oscillations. So from this graph, from this waveform, we can say that my sigma either it should be lesser than 0 or it should be equal to 0. Then only you will get, the system will remains in the stability. We will still elaborate this. From the figure we can see that we can conclude that the whole stability depends on the value of sigma. The sigma as either should be negative or equal to 0, because oscillation we should not leave, the oscillation should increase, either it should decrease or it should be sinusoidally sustained sinusoidal oscillation. So when it will be possible, when sigma is lesser than 0 or it's a negative, or when sigma is equals to 0. Now S equals to the same thing, dou p by dou delta divided by em. Now when this equation, when this is positive, when dou p by dou delta is positive, you will get two roots, s equals to plus or minus j omega. You will get the pair of complex conjugate roots. So under this situation, under this condition, you will get sustained undamped oscillation. So it is now, if it is a positive, so square root of minus of this value. Now when this value, synchronizing coefficient, when this value will be negative, so you will get negative into negative. Here you will get negative into negative, you will get the positive. So then you will get one positive real root and one negative real root, which indicates one positive root means my sigma is greater than 0. So now we can state the condition of the stability. If the system should be stable, synchronizing power coefficient should be greater than 0. This is most essential. If I want to say the system should be stable, my synchronizing power coefficient should be greater than 0. Now, yes, dou p by dou delta, evaluating at delta equals to 0 initial operating condition, it should be my p max cos delta naught. Now, what is my cos? Yes. Now what is my cos delta? If this item has to be positive, my delta should be lesser than, delta naught should be lesser than 90 degree. If it is more than 90 degree, my this term will become negative. This term, if it is more than 90 degree, my this term will become negative and becomes unstable. So what I mean to say is, always the power system should be operating at a delta be less than 90 degree. If it is more than 90 degree, this term becomes the negative and the power system becomes unstable. Now the synchronizing power coefficient, thus the synchronizing power coefficient PS should be greater than 0. Now what we have assumed that we have seen that initial operating point. So I will tell yes. Yes. Now I will get the maximum power. Now here at yes. Now here the maximum power will be occurred. This is my one minute. Yes. Let us say this. Now it is delta value or initial operating condition. Now as I said, this value should be less, this value should be more than the 90 degree. If it is more than the 90 degree, my unstable, the system comes to the unstable. So finally the power reaches to 0. If this is reaching to the 0, the whole power system will be collapsed when it is greater than 90 degree. But can I operate till 90 degree? Is it possible? So can I operate at delta equals to 90 degree? Is it practically possible? No. In reality, the power system will be operating at maximum 25 to 30 degree. 25 to 35. In reality, the power system will be operating at delta equals to 25 to 35. The reason is that if any disturbance occur, if I am operating at this point, if any disturbance or if any minor disturbance occur, there is a chance of the delta will be increasing, and once it comes to this place, now as delta increases, my power going to collapse. So we will operate this at this point also. Even if a disturbance occur, the delta may increase till here. It cannot go beyond this. So because of that reason, we are operating, or the initial operating of the delta is 35 maximum. So why we are not operating at above 80 or 85, even though we will get the maximum power here, unfortunately, if any disturbance occur at this point, there is a chance that the voltage will be collapsing or the power will comes to 0. It is, as we know that it is difficult to raise the power, but it is very easy to power to be 0, because it after 90 degree the power will be decreased gradually to 0. It is just like it is difficult to climb the steps, but it is very easy to down the steps. The same concept here. Okay. Now we will end this topic. In next class we will see the problems on this. Thank you.